Hello and welcome to week 3 of online learning. So this week we're going to do things a little differently than we did in week 1 and week 2. So this is the first week that we are going to learn something new. So this is the last section of Algebra 1. Everything we did in week 1 and week 2 of online learning were concepts that you had learned before. So today is the first time that we're going to learn something that you hadn't learned before this year. So what we're learning today is called exponential growth and decay, and there is no better way to show what this means than what we're going through right now in the world, which is the coronavirus. So how the first video notes are going to work is on your It's Learning, there is a PDF right underneath this video that has questions that tie to this video. So you can look at those questions and answer them as you watch, or at the end of the video, you can go back and answer those questions then. So either way is fine. So what we're talking about today is called exponential growth and decay. So what we're doing here is learning a little bit more about the coronavirus and how it spreads and how that ties to math. So I am not a biology teacher. I'm obviously a math teacher. But to make everything make a little bit more sense, we're going to go through a little bit of background on what the coronavirus is. So first of all, coronaviruses are a type of virus that circulate among animals, with some of them also known to infect humans. So a coronavirus is not new. There have been coronaviruses before. Some of them can cause disease. So what we're dealing with right now in the world is a newly identified type that has caused a recent outbreak of respiratory illness, now called COVID-19. So it's called COVID-19 because that stands for Coronavirus Disease 2019. So COVID-19 is new from 2019, but a coronavirus, that is not new. We've seen other coronaviruses before, things like SARS and MERS. Okay, so what we have here is that a couple weeks ago, some of you guys might have seen this picture on the internet where they said Lysol and Clorox wipes help fight human coronaviruses. So on the back of a Lysol can, you might see something that says helps fight human coronaviruses. And people were freaking out, like, how did they know about a virus that's brand new? We know nothing about it. Well, the truth is that coronaviruses are not new at all. The only thing that's new here is this new strand called COVID-19, which is the disease that comes from this type of coronavirus. Okay, so coronaviruses have been around for some time, but COVID-19, coronavirus disease 19, is what is new for us here. So how does this spread? COVID-19 is especially difficult for us to handle because how it spreads. So COVID-19 is spread by coughing and sneezing. So it is a respiratory disease. So if someone has coronavirus, COVID-19, and they cough and sneeze within a 6-foot diameter, so on each side 6 feet, someone else could pick up this here coronavirus. Okay, so you cough, you sneeze, you're out in Walmart, you walk by someone that just coughed or sneezed. If they had this coronavirus, then you would be very likely to catch this here. So it is spread by people who are coughing and sneezing, especially in public around other people. So what we're going to do today is look at cases of COVID-19 in Houston to help model this thing called exponential growth. So what we're going to do is we're going to go back to spring break when everything was normal. You were just out of school, you went to enjoy a week off, and no one realized that we were not going to go back to school after spring break for some time. So we're going to rewind back to Sunday, March 15th. So the data that I'm using here is approximated to show how this is exponential, but in a little bit I'll tell you what the actual exact numbers were. So what we had on Sunday, March 15th, was the first day in Houston that someone was tested with COVID-19. So it is true, we had one person, one case of COVID-19 on Sunday, March 15th. So that person went out into public or went to work or went to school, and that person spread COVID-19 to someone else. It is very contagious. They coughed or sneezed, and someone else caught it. So now on Monday, March 16th, there were 2 cases of COVID-19. So we were thinking, yeah, whatever, 2 cases, not a big deal. But then the next day, Tuesday, March 17th, 2 cases turned into 4 cases. People were still going out, they were seeing other people, and it continued to spread. So now we were at 4 cases of COVID-19 in Houston. Then the very next day, we were at 8 cases. The day after that, 16 cases in Houston. Then the next day, Friday, March 19th, 32 cases of COVID-19 in Houston. One day later, Saturday, March 20th, 64 cases of COVID-19 in Houston. So this is very bad because people are spreading COVID-19 and our numbers are increasing really, really, really fast. So it continued to spread and continue to spread. So let's look at the pattern of what happened here. So I'm going to look at this pattern in a table. So my initial day on March 15th, there was 1 case of the coronavirus in Houston, COVID-19, 1 case on my starting day, my initial day in Houston. 1 day later, there were 2 cases. That person and the next person went out and infected more people. 2 days later, there were 4 cases. 3 days later, 8 cases. 4 days later, 16 cases. 5 days later, 32. 6 days later, 64 cases. So we started with just 1, and only 1 week later, we now have 64 people with COVID-19. So let's look at this pattern. What is happening each day? So every day, what is the pattern of COVID-19 spreading in Houston? And the answer is that each day, my numbers are doubling. So every single day it's doubling. So if we continued this pattern, 64 would double to be 128 cases. Then the next day it would double to be 256 cases. This number is getting bigger and bigger and bigger every day because it is doubling, which means that my cases are multiplying by 2. So in just 1 week, we went from having 1 person with corona, COVID-19, to having 64 people with COVID-19. So that's really not good in the world of hospitals, the amount of hospital beds that are available. And this number just keeps multiplying times 2, times 2, times 2 every single day. Okay, so that's not good, not a good thing here. So let's look at the same numbers, but we're going to look at it on a graph to see the curve. So you might have heard in the news, everyone is talking about flattening the curve. Well, what is the curve? What are they talking about? So let's look at it on a graph. So on day 1, at the very beginning, March 15th, so day 1, my starting number was that we had 1 person that was affected by the coronavirus. 1 day later, so this is the days, and this is the number of cases. You guys don't have to write all of this down. You can if you want to, but the questions at the end of this will ask all of these questions here. So after 1 day, we now had 2 people that were infected by the coronavirus. After 2 days, we now had 4 people that were affected by this COVID-19. After 3 days, there were 8 people affected. 4 days, there were 16 people affected. 5 days, there were 32 people affected. And then 6 days, there were 64. After day 6, there were 64 people affected. So I took the table that we had on the previous page and I just graphed it. It said starting, so that's at 0, we had 1 person. Then after a day, there were 2 people. After 2 days, 4 people, 8 people, 16 people, 32 people, 64 people. So notice this curve is getting really steep, really fast. That's not good. That means that every day, twice, double the number of people are being affected. This is called an exponential graph. It is increasing exponentially. It's getting really, really big, really, really fast. So in Algebra 1, this is a lesson we've taught forever. So we've said, oh, look, coronavirus, exponential, we know what that means. So in the world of algebra, how an exponential growth function works is we start with a starting number, my initial means starting. So the number in front of the equation, so this here is the equation for exponential growth. This is really important today. You guys are going to need to know this formula. So what we have is we have a starting number, my initial value. So on this very beginning, we started with my initial value. Then we have something called a multiplier. So my multiplier goes in parentheses. So it's getting bigger and bigger and bigger and bigger and bigger. It's multiplying, it's getting bigger. And then my variable x is the number of times that this thing happens for. Okay, so this is what an exponential graph looks like. It gets bigger and bigger and bigger and bigger and bigger. So now before we left for spring break, we were practicing for your benchmark, your practice algebra 1 star test. And we told you that there's this word called asymptote. Asymptote. So an asymptote is a border that we cannot drop below. So if we look at this exponential growth function, my asymptote is this line underneath it. That line is sitting at y equals 0. My graph will never fall underneath the asymptote. It'll get really close, and then it'll get bigger and bigger and bigger and bigger. So this is what an exponential growth function looks like. So now let's look at Houston's exponential growth function to make it make a little bit more sense. So we said on our starting date, we had our very first day, we were off for spring break, one measly little person had COVID-19. There they were. That was my starting number, 1. But then every single day we multiplied by 2. It doubled, and then it doubled again, and then it doubled, and it doubled, and it doubled, and it doubled, and it doubled. Okay, so it got bigger and bigger and bigger. So that's called the multiplier. That's the number that would go in parentheses. This here is my multiplier. So then I have something called an asymptote. So my asymptote is y equals 0. So the reason why it's y equals 0 is because I can't have negative cases of COVID-19. So we said that the y-axis is my number of cases. So I can't have a negative number of cases down here. So that means that the lowest numbers are all above the asymptote. The asymptote is the border that my graph cannot drop below. Okay, so I start with a starting number. We started with 1 person in Houston, and then the numbers doubled every day for some amount of days. Okay, so this is what exponential growth looks like. We started a number, and it gets bigger and bigger and bigger and bigger and bigger really, really fast. Okay, so this is Houston's actual data. So the numbers that I picked before were approximate to show you what an exponential curve would look like. So do you see the curve here? So it started, and then we got more and more and more in this huge spike right here on March 29th. So on March 29th, we had a huge number of cases. That's probably because we had more tests and more hospitals available for people to get tested for COVID-19. But you can still see the curve. So we have a curve here that's getting bigger and bigger and bigger and bigger. This is called exponential growth. It grows exponentially. So now, in this picture of what happened, it was growing, it was increasing exponentially, but then something happened on March the 29th. So March 29th was a couple days ago. What happened a few days ago? So on March 29th, around that time, is when Governor Abbott said, whoa, 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 we need to start social distancing. When people are around each other, they are able to catch this virus because people are coughing and sneezing and germy. So people are getting the virus every single day. So if we start social distancing, meaning we're not around other people, then our number of cases will start to decrease. So instead of getting bigger every day, our numbers are going to start to fall because people aren't around each other to be able to catch this virus. So that's the big drop here that happened on March 29th in the city of Houston. So now let's look at some exponential growth around the world. So in the United States, look at this beautiful exponential graph. It started really small on March 1st, but then the cases of COVID-19 got bigger and bigger and bigger and bigger. This is exponential. It grew exponentially. Every single day, this number became larger and larger. So that's what the curve looked like in the United States from March 1st to April 1st. In just 1 month, there were over 20,000 people that caught COVID-19. So that's what happened in the United States. So let's look at Italy. Italy has also been extremely popular in the news because they had COVID-19 earlier than we did. So their cases started in February, and they too had exponential growth. It grew every single day from February to about March 15th. Now notice Italy is very small. Italy is right about the size of Texas. So compared to the United States, only about 5,000 people had caught it. So their growth was exponential though. It got bigger and bigger and bigger and bigger when they had coronavirus. But then they started social distancing as well. In Italy, people were not allowed to leave their houses. So people had to be stuck inside, and then look at what happened to the number of cases. It started to decrease because people were not outside spreading this disease, COVID-19. So we had an exponential growth in Italy that then started to decrease because of social distancing. So now let's look at France, another very popular country. France is also just about the size of Texas. So in March 1st, very few cases, but then it got bigger and bigger and bigger. Exponential growth happened with COVID-19 in France. Then again, theirs started to drop, probably because of rules with social distancing. Okay, so the phrase that you hear often here is called flattening the curve. So if you look at this curve, on day 5, we don't have very many cases. On day 10, still way under 50. Day 15, day 20. So the United States had to say, hey, we have to flatten this exponential growth. In the original curve, it got really, really big, really, really fast. So to flatten this curve, we need less people to catch it. It's still growing, but it's not growing nearly as fast. So their answer to be able to flatten the curve is to tell people, hey, we can't go outside and be with other people right now. We can't go to school because that would keep spreading and keep spreading and keep spreading. So by having less people around each other, then less people are going to catch COVID-19. It also means that hospitals can handle the number of patients for people that are older or have compromised immune systems. So if we flatten this curve, if less people are catching COVID-19, then we'll be able to go back to normal even sooner. So that's what they keep talking about. We're flattening the exponential curve so that we can then start to decrease our cases of COVID-19. So these graphs are exponential. This is called exponential growth. This is still exponential, but it's a flatter curve because less people are out in public able to catch COVID-19 from other people. So that's what we have here. So now we're going to talk a little bit about toilet paper, right? So what's happening with toilet paper in the stores? You're like, oh, this is silly. Why are we talking about toilet paper? But it's important in the world of this math lesson. So I'm going to make a table here to show you guys what's happening with toilet paper in stores. So again, we're going to go back to March 15th. This was my start date. On March 15th, I was hanging out in Mexico. Everything was normal, sitting on the beach. It was beautiful. Life was totally normal. But then what happened is I hear people at home are freaking out about toilet paper. I'm like, what in the world are they talking about? So on my starting date, March 15, there is, I'm just picking a random store here, and we're going to say that that store had 128 packages of toilet paper. But people are realizing, oh no, there's this global pandemic, we're freaking out, what's happening? And one day later, there are only 64 packages of toilet paper left in that store. 2 days later, 32 packages. Then the next day, only 16 packages. Then only 8, only 4, only 2. And 1 week later, we only have 1 package of toilet paper left to buy in the store. Which is true. So we started with a bunch of toilet paper when people didn't really care. But then as people are starting to get nervous about this global pandemic, they're buying toilet paper. So what is happening each day? So what is the pattern that you see here for my toilet paper that is available to buy in the store? What's happening is that it's cutting in half. We're multiplying by 1/2. So it's cutting in half each day. So in just 1 week, we went from having 128 packages of toilet paper on the shelf to only having one single package that's going to disappear really, really fast. So this here is also an exponential model. What this is called, it's not exponential growth, it's called exponential decay. I started with 128 packages of toilet paper. So A is my initial value or my starting number. So I started with 128 packages. B is my multiplier. My toilet paper packages are cutting in half each day for as long as we need it to, for X days, because people are panic buying and buying toilet paper. So I started with 128. After 1 day, it cut in half. After 2 days, that number cut in half. After 4 days, it cut in half. 6 days, it cut in half. And oh my goodness, there's no toilet paper left. So we started with 128 packages. My multiplier is that we're cutting it in half. My availability of toilet paper is being cut in half. And then X is the variable of how many days we have. So this is called exponential decay. It means my numbers are getting smaller and smaller and smaller by a multiplier. And this one, that multiplier was 1/2. It cut in half for each day. Okay, so the difference between exponential growth is growth happens when your multiplier is bigger than 1. So in this one, multiplier is the number in parentheses. So this one is times 4. So each day, my numbers are multiplying times 4. They get really, really big because we're multiplying times 4, times 4, times 4, times 4. So that is called a growth. It's an exponential growth. So now a decay happens when my multiplier is less than 1. It's like a fraction. 1/4 means it's getting smaller and smaller and smaller and smaller and smaller and smaller and smaller. Okay, so the difference between exponential growth and exponential decay is that in growth, we're multiplying. My multiplier is bigger than 1, whereas in decay, my multiplier is less than 1. So that is the difference between exponential growth and exponential decay. Okay, so and that's what we have for video notes 1. So you now know a little bit more about what a coronavirus is, what's the difference between coronavirus, and more specifically, what is COVID-19. And then we saw a model of what's happening with our cases of COVID-19 and what it means to start flattening the curve. So now you're going to go through your video notes and answer questions 1 through 12. So on your own sheet of paper, you're going to answer these questions. All of the answers were in this video. So according to the video, what is a coronavirus? How does COVID, coronavirus disease 19, how does it spread? Question 2. Question 3, in my approximate data, so in the very first data about Houston, how many people had COVID-19 on the starting day? So in Houston, my original slides, how many people had COVID-19 on the initial or on the starting day? In my approximate data, how many people had COVID-19 after 6 days? You can look at that table for my Houston approximate data. Question 5, what was the pattern for COVID-19 each day? The number of cases did what? Did they double? Did they triple? Did they quadruple? What happened in my Houston approximate data for my pattern in that table? Question 6, what is the equation for an exponential function? It's y equals something, something raised to the x. What is the original exponential function? What was the equation for Houston's exponential growth function that we talked about in my example? Which other countries showed exponential growth in this video? Most countries in the world have shown exponential growth, but in this video, which countries did we talk about? What is true about the multiplier in exponential growth? What is true about the multiplier in exponential decay? That was in that last slide. Draw a picture of what exponential growth looks like, and then draw a picture of exponential decay. Okay, so that's video notes 1. Then when you're ready, you're gonna head over to video notes 2, which is the same idea, but now we're calculating instead of graphing. And then you'll have video notes 3 for one more type of calculations. So I hope that you learned something today and that this was a useful lesson for you. I hope you feel a little bit smarter at the end of this. So go ahead and you can finish up video notes 1 and then head over to video notes 2. Have a great day. We will see you here soon.